Hello, everybody. So we are moving on to rational functions and their graphs. So there's quite a bit of stuff here that we actually have to cover. So let's get started. We are going to start with domain. So first off, we need to talk about what exactly is a rational function. Rational functions are quotients of polynomial functions. So basically, I've got a polynomial over a polynomial, which means that I can represent this in the terms of P of x over Q of x, okay? Um, so what we want to do when we talk about rational functions is we want to take a look at P of x, we want to take a look at Q of x, but the main thing for Q of x is, especially when we talk about domain, is that your Q of x can never equal 0. So if you have things in there that make that denominator ever equal 0, when we're talking about domain, we're going to have to exclude those values, okay? So let's take a look at this. We're going to find the domain of the rational function. So we're only looking at domain. And so since we're only looking at domain, we're going to look at this bottom value here. And so when I take a look at this, I want to know, is my domain, in this case x minus 5, where does that equal 0? In this case, this is going to equal 0 at x equals 5, which means my domain for this is negative infinity up to where I equals 0. And I'm going to union that, and I'm going to pick it up again, and I'm going to go to positive infinity. Okay, so when we're talking about domain, we only want to focus on the denominator itself. Now, if you take a look at this specific problem here, so this is where you need to be careful, because if you take a look at this top piece actually becomes x minus 5, x plus 5. Which means on the bottom, again, I have x minus 5, which means that this can cancel, leave me with an x plus 5. So a lot of you might think, oh, well, it's a line, and since it's a line, I don't have to worry about anything. It's going to be all real numbers. The answer is still no. Even though you canceled this piece out and this is all that you're left with, you still have that restriction because the whole function is this rational function as a whole. And so if you take a look at it and actually graph it, your graph is going to look something like this. And you need to pay attention to that little bitty piece right here. Because when you're sitting here looking at this is 1, 2, 3, 4, 5. So there's my 5, and at 5, I have that break. So just because it cancels doesn't necessarily mean that, okay, so I don't have to worry about the denominator anymore. The answer is yes, you still do, and this proves here why you have to. Okay, so we want to find the domain of the rational function of this whole thing. So again, I don't care about the numerator because I'm only focusing on domain, and domain deals with the denominator. So again, I'm going to take my denominator, x squared minus 25, set that equal to 0. Move my 25 over, and in this case, take that square root. And remember, when you take a square root, you get a positive and a negative 5. So again, so rational functions, and here's the other thing, rational functions always start off from negative infinity, and they come up to a number, do some stuff, and then they're going to leave to positive infinity. So you're always going to start with negative infinity and end with positive infinity. So in this case here, I start with negative infinity. I'm going to go up to my smallest number. In this case is 5. Union. I'm going to run from negative 5 to 5. I'm going to union again. And then I'm going to go 5 to positive infinity because I don't have any other restrictions. And both my negative 5 and my 5 have shown up. So this would be the domain for this one here. And if you take a look and actually graph it, it looks something like this. And so if you notice here at these green lines, that's the asymptote that your graph is actually going to run up along. Find the domain of this function. So if you take a look at this piece here, we're going to do the same thing. X squared plus 25. set that equal to 0. I'm going to move it over. X squared is equal to negative 25. Ooh, I cannot take the square root of a negative number. So this seems here I have no restrictions. And since I have no restrictions, I go from negative infinity to positive infinity, because there's nothing I can put in here that's ever going to generate a 0 at all. And if you take a look at the graph, oh, which I didn't graph, so let's take a look at that graph real quick. I thought I graphed it. I don't know why I did not graph it, so I'm sorry about that. So we're going to take a look at this graph and go on top. We've got, what is it, x plus 5. And then on bottom, we have x squared plus 25. And hit graph. Yeah, that's what I got. Yep, that's what I got. It's really hard to see, so let's kind of fix this window a little bit. We're going to fix our scale here. We're going to go from -1 to 1. See? And there you go. So you can see that there's no restrictions on that. It crosses the x-axis. There's no asymptotes or anything else like that. So that's what that's why we have from negative infinity to positive infinity. Okay. So now let's talk about vertical asymptotes, because this is where a lot of your problems are going to come from. They're going to come from the vertical asymptote piece. And they're going to actually have you start looking at coming from specific directions. So you're going to start seeing what's called arrow notation. So when you're looking at this, you have to pay attention to what it's asking you. So it's going to be asking you possibly one of 4 things. So on this first one, if you see X approaches A and there's a plus sign, means you're approaching it from the right. So if I've got this graph here, and let's say this is my asymptote right here, and we're running this way, this is what it would look like from approaching to the right, from the right. So you're going into that direction and you're reading it backwards. Approaching it from the left, so same concept. Okay, so we've got this asymptote sitting over here and we're approaching it from the left. So you basically read this one as normal because you're just reading it as it goes to towards infinity. Okay. And then these two here talk about end behavior. So this one, oops, well, I guess I'm going to go ahead and erase it. So these two on the bottom here, this is your end behavior. So as x goes to infinity. So basically what I want to know, as x goes to infinity, what's happening? Down here, x goes to negative infinity, what's happening? So basically I'm looking at my end behavior on these bottom two. Do I go off into an asymptote? Do I go off to positive infinity or negative infinity? Do I stop? Do I not exist? I mean, what's going on? So that's what these last two are actually talking about. So we have what's called vertical asymptotes. So when you're looking at these graphs and everything, and you're looking at these formulas, what you're going to be doing is you're going to wind up having either asymptotes or holes. And so what's going to happen is a vertical asymptote is what you approach at that number that doesn't exist. So if I'm sitting here doing this right here would be a vertical asymptote, because as my graph is approaching that, I'm actually going to run up along this and I'm never actually going to touch it. And eventually I'm going to cross over again, but not touching it. I'm going to jump over it and run off and do something like that. And so this vertical asymptote is like the no-no zone. Okay, so you can never exist in the no-no zone. So we have to look over that. When you're looking at specific graphs here as well, so I want to show you this as well. So if you have a graph And let's say we have this function here that's going to run up the y-axis. So it runs up this way and it runs up this way. Okay. When you're looking at this, you would say as x approaches 0 from the left side, that means my f of x is going, since I'm going up, is going to positive infinity. If I'm reading on this side here, as x approaches 0 from the right side, again, in this case, my f of x is going to positive infinity. Now, here's the deal. You don't have to run to just positive infinity, because you can actually go to negative infinity on the other side, and that's okay. So just remember when you're doing this, this is telling you, okay, there's probably an asymptote here because I'm looking at that number specifically. And if there's an asymptote, exactly what's going on. Am I going to positive infinity or negative infinity? So here's some more examples. So this one, as we're approaching A from the right, it's going to positive infinity, and the left going to positive infinity. And then from the right, you're going to negative infinity, and from the left, you're going to negative infinity. So those are the four options that sometimes when you that's actually some. Let's try this again. Those are the four options you have when you're actually approaching a asymptote. You're going to either run to positive or negative infinity. You'll actually never have a number here, so keep that in mind, okay? So how do we locate these? Well, when you locate vertical asymptotes, basically what you're going to do is take that q of x, whatever it is, and you're going to factor it. And then you're going to see if it cancels with anything in the numerator. So here's a note for you. So if your denominator ever cancels with your numerators, you don't have a vertical asymptote, you have a hole. And you're going, a what? You have a hole. So if we go back to the first slide that we looked at, this one here, notice how this denominator canceled with that numerator right there? Well, it created a hole in the graph, okay? Because I canceled, I created that hole. If they do not cancel, so if you cannot cancel anything with your numerator and your denominator together, wherever your denominator is at 0, those are going to be vertical asymptotes. However, when you're talking about domain, it doesn't matter. It doesn't care if it's a hole or an asymptote. It just wants to know what are my restrictions. So either way, you just have to be able to look at that and see. So find the vertical asymptotes, if any, of the graph of this rational function. So what we're going to do is we're going to only focus on the denominator right now. And so we're going to say x squared minus 1 is equal to 0. We have x squared is equal to 1. So x is equal to plus or minus 1. Now, I'm looking at my numerator to see if any of these will cancel, and there's nothing up here that's going to cancel. I can't factor this to get anything down here. So basically, I'm good to go. So that means because my numerator and denominator are not canceling anything, I have vertical asymptotes at -1 and +1. And if you take a look, that's what the graph would look like, -1 and +1. Okay. Let's try it again. Find the vertical asymptotes, if any, of the graph of this rational function. So again, I only care about, to start off with, I only care about my denominator. X squared plus 1 is equal to 0. X squared is equal to -1. Oops, can't have that. And so since I can't have that, that means there are no vertical asymptotes. And so since there are no vertical asymptotes, I just have this nice pretty little graph here. Okay. Now, oh, I missed one. If I have, let's say, g of x equals x plus 3 over x squared minus 9. Well, I've got x squared minus 9 is equal to 0. X squared is equal to 9, so x is equal to plus or minus 3. So that's my denominator. If I look at my numerator, ooh, I have an issue here because this is actually a factor. So if you stop to think, this x squared minus 9 is actually x minus 3, x plus 3. And then on top, I have the x plus 3. So if you notice here that this and this are going to cancel, so that means my x plus 3 is equal to 0. My x is equal to negative 3. This here is not an asymptote. It's a hole. So that means my vertical asymptote, my va, is only going to happen when x equals 3. And then I have a hole at x is equal to negative 3 because I wind up canceling. Okay? So the only vertical asymptote that's going to happen only when x is equal to 3. All right. Horizontal asymptotes. So just like with vertical asymptotes, horizontal asymptotes can also happen. And the nice thing about this, there's a quick and easy way to do it. So there's no factoring involved or anything else. What you have to do is you have to actually look at the problem and you have to look at a ratio. But horizontal asymptotes, what they look like is that you're going to actually have your graph as x goes off into infinity, we're going to level off. And that's what a horizontal asymptote is leveling off. Now, in the center here, when you're actually doing all the moving up and down, and you can cross your horizontal asymptote. Unlike with a vertical asymptote, you can never cross it. A horizontal asymptote, you can cross it, and that's okay. But what happens is we actually look at the infinity and negative infinity on both sides, and we want to know, are we approaching something? And eventually, if you wind up leveling out to something, that is going to be your horizontal asymptote. But if you just keep on going off without bound, so you're going off into positive infinity or off into a negative infinity, then you don't have any horizontal asymptotes. So how do we look at this? How do we know if we have horizontal asymptotes or not? You have a handy dandy little formula. So you're going to be given two polynomials over each other. What you need to look at is the highest exponent on both the numerator and the denominator. And that is the only thing you look at. And you're going to put them into this fraction form. And then one of three things is going to happen. If your numerator's exponent is higher than your denominator's exponent, you are either running off to positive or a negative infinity. Basically, that means you have no horizontal asymptote. If your m and n are the same exact thing, then you can actually reduce this fraction and those two will go away, leaving you with just a over b. Okay, so if they are the same, you're just going to simply reduce the fraction and your answer is just going to be the coefficients. If your denominator is ever higher than the numerator, then you actually are just going to have a horizontal asymptote at y equals 0. And you're done. Okay, so three different options. The numerator is the bigger exponent, then you're going off into some sort of infinity. If they are the same, it's just the ratio of the coefficients. And if the denominator is bigger than the numerator, you have y equals 0 as your horizontal asymptote. So let's take a look at this. So find the horizontal asymptote, if any, of the graph of this fractional function. So I only care about the highest exponent on the numerator and the highest exponent on the denominator. So I'm going to take 9x squared and put it over 3x squared. Then I'm going to take a look at their exponents. Since they're both the same, I'm going to go ahead and reduce this fraction here, and I'm going to just wind up with the 3. So I have a horizontal asymptote at y equals, I was almost about to put x, but as y equals 3. And if I was to graph this, that's what I would get. So if you notice here, I don't care about this middle piece. This piece I don't care about. What I care about is what's happening as I'm going off without bound. Am I leveling off somewhere? Okay. Now, here's an interesting thing about this. You can actually have two different horizontal asymptotes, and that'll be okay. I don't think we have to worry about that in this section, however. But what you're going to do is you're going to look at coming from the left side and going off to the right side. That's when your x goes to infinity and then y or x goes to negative infinity. That's when you're going to look at those horizontal asymptotes there. Okay. So then, let's try another one. Same thing, 9x over 3x squared plus 1. I want to find that horizontal asymptote. So when I'm actually doing this, I wind up with this as my fraction I'm going to look at. I notice that my bottom is bigger than my top in terms of the exponent. So that just means that I'm going to have a horizontal asymptote at y equals 0. And if you was to graph it to see what it looks like, there you go. So again, notice I don't care about this middle piece, but as I'm running off into infinity, I'm slowly approaching that 0. Find the horizontal asymptote, if any, of the graph 9x cubed over 3x squared. So I've got 9x cubed over 3x squared plus 1. I only care about the highest exponents on each. Notice that my numerator is higher than my denominator. So I'm going to run off into infinity, depending on which way I'm going. And so if I take a look at this, there you go. And so how do you figure out where, if you're going off to positive infinity or not? So when I'm looking at this, as x gets bigger, what's happening to my y? I'm going to pick a big number, okay? I'm going to pick it doesn't matter. I'm going to pick a positive number here, and I'm going to put a positive number here. So if you think about it, if I took x cubed and I made it, let's just say 15,000, but it's a positive number, I remain positive up top. I take that same 15,000 and put it on bottom. Again, when I do all the math, I wind up with a positive number, so I'm running off to positive infinity here. When I do the flip side, however, if I put in negative 15,000, well, a negative cubed is going to give me a negative number, but a negative squared is going to give me a positive number, so I have a negative over a positive. So as my x goes off to negative infinity, my y will go off to negative infinity. And you can look at that and see, based off this graph right here, we're going down that way and going up that way. Okay. So when you're just taking a look at this or whatever, just pay attention to what it's asking you to do. And if it looks at, when you get to this portion here, if you're not really sure what to do, just pick a positive or negative, it doesn't matter, and just kind of evaluate. Remember, the odds here, if you put in a negative, you're going to get a negative back. And even if you put in a negative, you're going to get a positive back. So that's just kind of one of those key things that you kind of need to remember when you're working through this, okay? All right. Let's find some x and y intercepts. So this is not as bad as it sounds. So you remember x-intercepts are where you cross the x-axis, and y-intercepts are where you cross the y-axis. If you're given this problem, this could look kind of daunting, but remember, your y-intercepts happen when your f of x is equal to 0. Okay, so what you're going to do is you're going to evaluate this at f of x equals 0. And so you're going to say 3 times 0 minus 3 over 0 minus 2, which winds up with 0 minus 3 over 0 minus 2, which winds up with negative 3 over negative 2, which winds up to being 3 halves. So my y-intercept happens at 0, 3 over 2. Okay. My x-intercept happens is when my f of x equals 0. So I'm going to take this and I'm going to say 0 is equal to 3x minus 3 over x minus 2. Now here's a neat thing. I'm going to cross multiply these. And when I cross multiply these, this x minus 2 goes away, leaving you with just your numerator. So when you are solving for x-intercepts, it's just the numerator. So you actually are going to solve 3x minus 3 is equal to 0. Move my 3 over and divide. So I have an x-intercept at x equals 1. Okay? So that means when I'm at 1, my y is 0. So that's how, when you're looking at x and y intercepts, that we are going to approach it. Now this one's an easy one where everything is kind of worked out for you. Then you have a problem that looks like this. Don't let that scare you, okay? So when you're taking a look at this, well, let's start off with finding our y-intercept. So that happens when f of 0 happens, right? Well, if I put a 0 into here, 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 and here, I'm only left with that piece right there. Well, negative 12 over negative 2 is a positive 6. So I have a y-intercept at 0, 6. For my x-intercept, again, I only care about the numerator. So I'm just going to set the numerator equal to 0. X squared minus x minus 12, and set this equal to 0. And then I'm going to factor. Well, that's x minus 4, x plus 3. That equals 0. So I have x-intercepts at 4 and negative 3. So I have my x-intercepts at 4, 0, negative 3, 0, and I have a y-intercept at 0, 6. Okay. So again, finding x-intercepts, you're going to set your numerator equal to 0. Finding the y-intercepts, basically cross off all the x's, and it's just going to be your constants that are left over. All right. Let's talk about slant asymptotes. This might be the only new thing that you will probably have seen. So, slant asymptotes. So the graph of a rational function has a slant asymptote. So this is the key. If this doesn't happen, you don't have a slant asymptote and you don't have to worry about it. It has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So that's what has to happen. If your numerator is 1 degree more than the denominator, you have a slant asymptote, which basically means you don't have a horizontal asymptote. All right, so keep that in mind. You do not have a horizontal asymptote. You will have either a slant asymptote or you will have a horizontal, but you can't have both. So the degree of the numerator is 1 more than the degree of the denominator. So the very first thing you're going to do is you're going to take a look at your problem and say, okay, is my numerator 1 more than my denominator? If the answer is yes, you have a slant asymptote. And so then there's some things that you need to do. You need to factor this down, either using long division or synthetic division. In this case, because we have that linear right there, we can actually do synthetic division here. So I know I've got a 2, and then I have a 2, a negative 5, and a 7. And I have my little box right here. And I drop down my 2. So 2 times 2 is 4. Combine them, negative 1. 2 times negative 1 is negative 2. Combine them, and I get a 5. Okay? So now, that means I have 2x minus 1 with a remainder of 5 over x minus 2. So when we are talking about a slant asymptote, what we are going to be looking at is we are looking at this piece right here. That is your slant asymptote. So you do not look at the remainder when you're talking about a slant asymptote. So if I was to graph this piece right here, and then I graph this 2x minus 1, you will notice that my 2x minus 1 is going to be a line that my actual problem is going to be running off of. And so if you take a look at it, here's my y1, which is the actual problem. Here is my slant asymptote right here. And so if you take a look at it, you will notice that we are running off into that slant infinity off of here. So yes, I'm running off to positive infinity going this way and negative infinity, but I'm doing it at a specific pattern. Okay, so you're doing this at a specific pattern. And so that's how you find slant asymptotes, is that you go ahead, you're going to long divide it out, or you're going to synthetic. It doesn't matter which one, but either way, you're going to look at that line there, and it's going to tell you what your slant asymptote actually will be. Okay. All right. So that is it for rational functions and their graphs. So please, if you have any questions or anything, make sure you are emailing me and sending me reminders or whatever else. And if there's nothing else, I hope everybody has a wonderful day. I will talk to all of y'all soon. TTFN. Ta-ta for now.